Well, first thing you should notice is that I'm not Lori Figge. This is her talk. I am the second person on that list in a team effort. I am the PI for this instrument, the ALICE UV spectrometer on Rosetta. For those of you that don't know the secret, PI actually stands for Principal Instigator. It's the one that gets people to do things. And when we first got into orbit back in August, I wanted to make sure that we had a good turnout with results at DPS and at AGU. And so we put together a couple of clutches of talks. Lori agreed to put in an abstract. What I didn't know was she was going to ask me to take the trip and give the talk for her. But I'm doing that. There's one other thing. I think getting to follow the previous talk, I would like to do something I've always wanted to do. If you got 3D glasses, you will not need them for the UV talk, but please put them on. I've always wanted to see an audience full of people doing this. You could even take a picture. It's pretty cool. Everybody put them on, and then we'll get a picture, and I bet you it goes viral. So, you do look cool. There he is. Okay, let's get to the meat of this. So I'm going to talk about the ALICE ultraviolet spectrometer on Rosetta. This is the first in a line of ultraviolet spectrometers that include instruments on New Horizons, on LRO, on Juno, and on future missions such as JUICE as well. So this is an imaging spectrometer, and let me use the pointer. This is a picture of the device with the technician behind it. There is a telescope that feeds a spectrograph. This is the reflection grating. And then there's an electronic detector called a microchannel plate that produces a two-dimensional spectral and spatial image in the far ultraviolet. I'll show you more about how the data works. You can see it's a pretty small instrument. It only draws 4 watts. It only weighs 3 kilos. But it's a very powerful instrument, particularly for studies of the coma. In fact, the 4 primary objectives of ALICE at CG are shown right here, and 3 of the 4, shown in blue up top, are all about the coma, about noble gases, about parent molecules, about the atomic content of the coma. We have secondary objectives. They're mostly about the coma as well, studying fine dust that we can do very well in the ultraviolet, studying the ionized tail, etc. But we also have an important objective shown there in the 4th bullet, which is to make far ultraviolet studies of the surface of a comet. And in fact, although Paul Feldman's going to be up here next and talk about some of the earliest work we've done with coma activity, we're really waiting for the main event, for the water to turn on and for the comet to get a lot more active and the coma to be much more interesting in this bandpass. And so what Lori's done and the work that I'll be reporting on are studies of the reflectance properties of this comet. And I should tell you, this comet and this investigation is making the first FUV studies of any comet, because the cometary nuclei, combined with their small size, combined with the faintness of the sun in this wavelength region, makes it impossible for Earth-orbiting satellites to study these reflectance properties. And it's complicated further by the fact that the coma, when it's active, when the comet's closer to the sun, presents emission lines and dust and other complications. So this is really an opportunity for the first time to make detailed studies, and because we're close, we can even make spatially resolved studies of the surface and look for variegation. So the observing strategy is pretty simple. We make time exposures. We call them histograms. They're essentially this 2D spectral versus spatial image. And we began doing that in August, right when Rosetta entered orbit around CG. We typically make 5 or 10 minute histograms. We make very many every day. We don't use very much data volume, so we're able to operate the instrument quite a bit day in and day out. Now, we do have a paper that's already been submitted. I'm actually the first author of this part of the work, and it's the stuff that's highlighted towards the bottom. I'll say very briefly what this is about because it leads into what Lori's doing. And this is work that I reported on at DPS. So we made spatially average studies as the comet was rotating under our field of view back in August for 3 days. And we added up all the signal, and we got the FUV spectrum that's shown there In black, that's the reflectance after you divide for the sun. And we found some interesting things. First, we found that the reflectance is very low. It's between 1% and 2%. It's very hard to imagine how you make materials that black in the FUV. There's nothing in our spectral atlas that is that dark. There are things that are a few percent reflective, but not that reflective. So we think that it's a combination of very dark materials combined with a porous surface that acts as a light trap. Additionally, notice that on the red, that is the right-hand side, the reflectivity is lower than on the blue, the left-hand side. That blue spectral slope was another surprise, and it could be due to fine particles that are Rayleigh scattering in the surface. Or it may be due to what the comet's made of. And we're still talking about what that is, but we do know that we can get a pretty good fit. It's non-unique, but it's very interesting. It's a fit that's made almost entirely of tholins, almost no water ice. In fact, we only need about 0.5% water ice aerially in the mix to make this fit. This is a spectrum of water ice in blue right here, and you can see the comet looks nothing like it. Formula, we need about 0.5%, and we need to put in that darkening agent because we can't find materials that make it sufficiently dark. So that's work that's grand sum and spatially averaged. What Laurie started to do with data taken in September and then again in November is to go to the next stage, to start to look at the photometric properties and the phase curve of the comet, and to look for spatial variegation from place to place rather than doing the averaging. So these are the details of the observations. I'll let you read them for yourself in terms of heliocentric distance, how far the spacecraft was from the comet, what the phase angles were, etc., and get right to showing you some of the data. So our slit looks, we call it a dog bone. It's got a narrow region in the middle, and that gives us higher spectral resolution, which is important for some of the gas phase studies. And then at the top and bottom of the slit are these wider regions that we use to let in more light when we don't have signal to noise. But for the purpose of the studies of the cometary surface, it's a little bit irrelevant. We get signal here, we get signal here, and we get signal here. We actually have about 20 spatial channels across the length of that slit, so we can see from place to place. And then the comet rotates under the slit. And when we get a spectrum, this two-dimensional thing is wavelength going left to right along the abscissa. And then this is the spatial dimension along the slit. At this wavelength, which is actually Lyman alpha, solar Lyman alpha reflecting off the sun, you can actually see an image of the slit. You can even see it's narrower here than it is here. Out here, the sunlight is much brighter at the red end than at the blue end, so you see the continuum. And this is the top of the comet and the bottom of the comet where the signal stops. And off the comet, you don't see very much in the way of coma. And actually, this is a dark region of the, this is Laurie's talk, so I should say this is a dark region of the detector, and forget what I just said. So Laurie has begun to compare different regions on the surface and has found that, in fact, in the ultraviolet, we are seeing differences in spectral slope from the head to the neck to the body. And that is surprising to us. We would have expected very naively that the comet would be one homogeneous body with relatively homogeneous reflectance properties. But that's not what we're finding. And when we look at even higher resolution, either time resolution, where we can look at smaller regions, or spatial resolution, we should expect maybe to see even more kinds of variegation. But we're already seeing, and you can see in these two spectra that she's presenting, that this spectrum is substantially more blue slope than this spectrum. One made here, the other made here, and that's a preliminary result, but that's interesting. She's also starting to develop the phase curve for the comet, and she's broken it down into 3 wavelength bins, but you can see that they all behave relatively similarly, that the comet is, as you would expect, as you go to smaller phase angles, brighter and brighter. We haven't yet gotten down into the region that one would normally probe from the Earth, down inside of 20 degrees and 10 degrees even. But already we're starting to see some interesting things, and we can compare this in a preliminary way to the sort of taxonomically to phase curves of other objects like asteroids that have been observed in the visible and in some cases in the ultraviolet by IUE and by Hubble. observatories. And we're finding that it's in family, but this is very early. And what we're most interested in doing is getting the spatial variegation combined with the additional angular coverage down at small phase angles to see how the comet is similar and how it's different. So far, we're just finding that we do see the phase curve and that it's not, that it's in family with other small bodies. So that's the report that she wanted to make. I want to thank the Rosetta project and NASA for support for a tremendous mission to be a part of. And thank you, and I'll take any questions. Thank you.
Any questions? Can I shout it out rather than get...
Go ahead, Carrie.
It looks like in the, I think, the spectrum of the head versus the neck, there was an 1100 angstrom feature. May have been one of the spectrum versus the other. Is that significant and real?
Yeah, I know what you're talking about, and that's actually a feature that we see when we don't get a good division between the solar spectrum and the cometary spectrum. The solar spectrums that the solar spectra that we use come from other observatories. They don't come from the instrument itself. They're made through a different optical system, and when we don't get that just right in a quick and dirty, and that may be what you're seeing. We see it a lot.